So we'll do 10, 11, 12, 13, 15, and 16. And let's start with question number 10. Those, by the way, are in your textbook, and you will find them on those pages 198 to 199. So I start with question number 10. You have a sealed bottle and it contains air at the temperature of 22 degrees. So we could say the temperature is 22 degrees Celsius. We want to convert it into Kelvin, so we plus 273. So that bottle contains air at the temperature of 295 Kelvin. And this is at a pressure 12 times 10 to the 5 Pascal. That's what they say. Now, the temperature is raised. So from a temperature 1 and a pressure 1, you get to a new temperature 2. And it's raised to 120 degrees Celsius. So now you have 120 degrees plus 273. The new temperature is a 393 Kelvin. And we're looking for the new pressure. You can see the temperature has been increased, and therefore the molecules, the particles in the substance are going to move faster now. They will have a greater kinetic energy, right? And therefore we expect to have more collisions to the walls of the container, and therefore you expect the pressure to increase. But let's see exactly how. So you have learned this equation, P times V equals nRT, right? Where P is the pressure, V is the volume, N is the number of moles, R is the gas constant, and T is the temperature. But we can apply it here. I can write P1 V1 equals N1 T1, and P2 V2 equals N2 or T2. But of course, let's divide those two, because the volume cancels out. It's the same volume. We're talking about a sealed bottle, and therefore it has the same volume and the same number of moles. The constant, the gas constant, is the same, and therefore we can write that P2, if we solve for P2 here, it would be P1 times T2 over T1. And using the numbers that we're given, P1 is 12 times 10 to the 5 pascals, and you times this by the ratio of the temperatures 393 Kelvin and 295 Kelvin. So finally, using your TI-84, your calculator, you will get that the pressure, when the temperature increases, will indeed be a little bit higher, and it will be 16 times 10 to the 5 pascals. And that is your final answer for question 10. Now, I'll take question 10 a little bit higher up so we don't see it, and we will solve question 11. Question 11 says, a gas has a pressure of 8.2 times 10 to the 6 pascals. Let's write this down. 8.2 times 10 to the power of 6 pascals. And the volume of that gas is 2.3. Let's write it here. Maybe the times, I'll make it as a little x. Why not? So 2.3 times 10 to the power of negative 3 cubic meters. And now it says the pressure is reduced. So if this one was P1 and V1, you reduce the pressure to P2, and the new pressure is 4.5 times 10 to the 6 pascals, and it's asking for the new volume. And you know that you have constant temperature. It says so, the temperature is constant, and we're talking about the same gas, so therefore you have the same moles, right? the same amount of substance. So let's find the new volume. Again, P1V1 equals nRT1. P2V2 equals nRT2. You divide both sides, and temperature is the same, gas constant is the same, number of particles is the same, and if you need to solve for V2, V2 will be P1 over P2 times V1. So, if you use the numbers and you substitute here, you will get that V2 is 4.2 times 10 to the negative 3 cubic meters. There you go. So this was question 11, and this is the final answer for question 11. Now, I will take both of those two questions higher up here, maybe even a little bit more, and let's solve together question 12. Maybe here, that's a good spot. So it says, a mass of 12 kilos of helium is required to fill a mass of 12 kilos of helium is required to fill a bottle of volume 5 times 10 to the negative 3 cubic meters at this temperature. Determine the pressure in the helium. So, first of all, let us see. You know, helium has 2 protons and it has 4 protons plus neutrons, okay? So we know that the molar mass of helium is 4 grams per mole. We talked about this, is this number that is approximately the molar mass of helium. Now, if you have 12 kilos of helium, we can calculate how many moles you will have. So we said N is, that was in a previous lesson, and the number of moles is the mass divided by the molar mass. And if you have 12 kilos of helium, so let me just write 12 times 10 to the power of 3 grams divided by 4 grams per mole, you can actually calculate that in total you will have 3 times 10 to the power of 3 mole. Alright, we know this is the number of moles. Now, from the gas laws, you have PV equals nRT, and they're asking you for the pressure. So the pressure P is going to be nRT over V. And if we go back and we look, it tells you exactly what's the temperature. Of course, we need to convert it to Kelvin, right? And it also tells you exactly what's the volume. So we will now do the substitution. Good. Let's go back. So the volume, I'll start with that because I remember the number, is 5 times 10 to the negative 3 cubic meters. The number of moles are 3,000. I'll just write it here because I have it ready. And the constant R is 8.31. If you're wondering where you can find the constant R, is in your formula booklet. It's here, gas constant R. It's 8.31 joules per Kelvin per mole. So let's go. 8.31 joules per Kelvin per mole. Oops. And then you need to times by the temperature. The temperature was 20 degrees Celsius. If you plus 273, that becomes 293 Kelvin. So if you do this calculation, you will find that the pressure in pascals is 1.46 times 10 to the power of 9 pascals. There you go. So this is the answer on question 12. Let us go and solve question 13. So maybe I'll just write it here. Question 13 says, determine the mass of carbon dioxide, molar mass 44 grams per mole, required to fill a tank of volume blah at a temperature blah and pressure blah. So similarly to the previous question, if you have 12 kilos, okay, so now we have to find the mass of carbon dioxide. So what if we first find the number of moles of carbon dioxide? And then we can times that by the molar mass. Let's do that. So that was 13. PV is nRT, and N is PV over RT. Now we can use our numbers. The pressure was 4. Was it? Let's see. It was 4 atmospheres. So we need to convert atmospheres into pascals. And the way that you do it is it's 4 atmospheres times 1.013 times 10 to the 5 pascals. That's the conversion. And you times by the volume. The volume is 12 times 10 to the negative 3 cubic meters. And you divide by the gas constant. That was, let's take it from here. A little bit lazy, but it's fine. So I'll take the gas constant. There you go. Times the temperature. The temperature was 20 degrees. So in Kelvin, 293 Kelvin. And the number of moles is 1.998 mole. That's what you will get, right? Now, remember, the number of moles, N, equals to the mass divided by the molar mass. So the mass of carbon dioxide is the N times mu, right? The molar mass, which is 1.998 mole times, what was it? 44 grams per mole. We were given that. So the mass of carbon dioxide, it will be 87.9 grams. And this is your final answer to question number 13. And we have 2 more questions to go. So I'll take this one a little bit higher up. By the way, I will send you this document right afterwards. Maybe, just by looking at the solution, you can understand. You don't have to watch the video in the future. Question number 15. It says the point marked in... maybe I'll solve 15 on the actual paper here. The point marked in figure 9.18, so this figure over here, represents the state of a fixed quantity of ideal gas in a container with a movable piston. The temperature of the gas in the state shown is 600 Kelvin. So you have this is P, this is V, and the temperature here is 600 Kelvin for this dot, right? Copy the diagram, sure. Indicate on the diagram the point representing the new state of the gas after the following changes. A. The volume doubles at constant temperature. So let's write the equation of state. PV equals nRT. Okay. So if the temperature is constant, the R is constant and the N is constant. When the volume doubles, so when V becomes 2V, in order to maintain the same product, nRT, the temperature has to, the pressure has to halve, right? Because now this is how you keep the equation balanced if nRT are constant. So if the volume doubles, the pressure halves. So how could that look on the graph? Let me just clear this out. So when the volume doubles, so if this is your initial point, you double the volume, so you go here. But the pressure needs to halve, so actually it has to go here instead. So the new point will be somewhere here, where it has, if this point is the PV, this point now will be the P over 2 and 2V, okay? Let's answer with blue, B. B says the volume doubles at constant pressure. So the pressure now will remain constant. So let's write again the equation. PV equals nRT. The pressure will be constant. N is constant, R is constant. So when the volume doubles, the point will be here, because now you will have the same pressure and double the volume, right? So the same pressure as the original, and I mean it should be on this line, right? And then the volume doubles. That's what's going on. So that was B. So let's say this is B and this was A. And let's choose a different color so we can do C. I'll choose green now. It says the pressure halves at constant volume. Well, that's easy. So the pressure halves here at constant volume. So this is C. Okay? And that's about it. I don't know if you recall, we said that when the temperature is constant, and I'm referring to A, then the points are all located in a curve that we call it isothermal curve. And we said that isothermal means constant temperature in a way. So you can clearly see here that C has a different temperature and B has a different temperature because they are located on different isothermal curves, right? Anyways, let's solve 16 finally, and I will do it up here. Question 16. It says two ideal gases are kept at the same temperature in two containers separated by a valve that is shown in the following figure. Estimate the pressure when the valve is opened. So you have the information of each of the containers here, and we will have a small strategy here. So when you look at each of the containers separately and you use this equation that we learned, PV and RT, the equation of state. Let's work with one of the containers. So P1 times V1 is going to be N1 R T1. And I will isolate N1 here. N1 will be P1 V1 divided by R and T1. If I'm not mistaken, it says constant. Yeah, they are kept at the same temperature. So, we need to keep that in mind. The temperature stays the same. So I'll just, we just need to remember that R and T1 are constant, right? Now let's work with the other container. So similarly to the first one, the other container will also have, now we call it P2, V2, N2 R T2. So N2 will be T2 V2 divided by R T2. So when you combine the two containers in the end, they will have, let's fix that, they will have now N1 plus N2 number of molecules, right? And the volumes will be added. So the volume will be, that's going to be equal to a new pressure. We don't know the pressure. That's what we're looking for. But the volumes will be added. And the temperature, it says it remains the same. So what if I just write it as T all over like that? So we can create an equation that P1V1 over RT plus P2V2 over RT is going to be equal to the final pressure V, V1 plus V2 divided by RT. And we can simplify, RT simplifies everywhere. And if you use the given numbers, you can actually isolate your P and calculate it. So the final pressure in the two containers will be P1V1 plus P2V2 divided by V1 plus V2. So let's use our numbers. What are the pressures here? Let me just see. 12 atmospheres and 6 atmospheres. Right. Should we find our final result in that? No. Okay. So, yeah. And the volumes are decimeters cubed. So, but that's okay also. We could just say 9. Okay, let's fix this. So, both the volumes, when you add them, is 9 dm cubed. And then your pressure, P1, is 12. 12 times 12 actually atmospheres times the first 6 dm, so 6 dm cubed plus 6 atmospheres times 3 dm cubed. There you go. And you will do the calculation here. You will find the pressure in atmospheres. And that's about it.